Welcome to EQ1 of Coastal Landscapes and Change. So this is the first section of the coast topic that you studied in Year 12. And EQ1 asked, why are coastal landscapes different and what processes cause these differences? Reminder, as with all of these recordings, that this is not replacing what you have done in lessons when you did this topic. This is just to reinforce the main ideas behind the topic and is good use as a revision summary for the entire topic. Today we're going to look at just EQ1, and you can use the coasts revision booklet that you've been given along with this to help you. So the first thing we looked at in coasts is the shoreline and what we call the littoral zone. Now the littoral zone is very simply the breakwater area. So this is where the waves come on shore. It's the nearest to the coastline where high and low tides happen. So there are four main sections, if you like, to the littoral zone. There's the offshore section. This is the furthest section of the littoral zone out to sea, and this is the deepest area where waves start to break. Then we've got the near shore, which is closer to the coast, and this is an area of shallow water and it's beyond the low tide mark. So there is more friction in this area between the seabed and the waves, and that distorts those waves. It's the break zone. Then we've got the foreshore zone. Now the foreshore zone is the area between high and low tides. So this area is covered in water during high tide, and then it is exposed, as you can see in the image there, during low tide. And then the back shore is the area above the high tide mark, and that's affected by wave action only during storm events. So the back shore may be covered by the seawater during stormy events, where the wind is pushing the waves onto the coastline, but generally it is not covered by water. And then you've got your cliffs and your general posts that we build on behind that. Now, there are different types of coastlines formed by this littoral zone. Because of the processes of the littoral zone, because of the erosional and depositional processes, we get different types of landscapes, and we can see that they're different by the formation of rock at them. So the first type of coast is a rocky or a cliffed coastline. And these are usually in areas of high shape of the land or high relief, usually have resistant rock. They are high energy environments, and erosion in these places is greater than deposition. And you usually find destructive waves at these types of coastlines. And you can see there in the image on the bottom left, the type of coastline we're talking about here. So even though erosion rates are high, erosion overall actually takes a long time for this type of rock. Then we have sandy coastlines. Now these are generally at low relief areas. They're gently sloping. There's soft rock here. Deposition is greater here than erosion. So there's lots of deposition taking place by the coastline, by the sea, because of constructive waves. So they have a strong swash and a weak backwash. And then we have estuarine coastlines. Now these are low relief coastlines with salt marshes, as you can see in the image there. The reason they are estuarine is because they usually are at a river's mouth. So deposition is also greater than erosion here, and it's a low energy environment with soft rock. And there's one thing to consider at all of these types of coastlines, and that is the dynamic equilibrium of the coastline. The balance between the inputs of sediment, the outputs, and the flows of sediment that exist because of the energy that exists at the coastline. So we can also see longer term changes at coastlines, such as sea level change and sea level rise. And that also affects the balances or the dynamic equilibrium between the inputs, flows, and outputs. And you could also factor in more local changes like high and low tides, weather conditions, varying wave energy, as impacting on that dynamic equilibrium at a coastline. Now, we can classify coasts in terms of short-term and long-term classifications. So let's start with the short-term classifications of coastlines. So things that happen in the short term is tides from energy inputs, so the ebbs and flows, the highs and lows of those tides over a 12.5 hour period during the day, as well as current type and river flows and the amount of precipitation and gravity and tectonics and the change of those. And that creates our high and low energy coastlines overall. We've also got sediment inputs over the short term classification period. So deposition and erosion rates. If the deposition rate is higher at a certain point in time, that means the coastline is expanding, it's growing in size. If erosion rates are higher, that means the coastline is receding, it's eroding in that short period of time. And linked to that, we've got advancing and retreating coastlines. So erosion and deposition affect whether a coastline advances or retreats. And that also impacts whether the coastline is emergent or submergent. And that's linked with sea level rise too. So if the sea levels rise dramatically, you may have a submergent coastline. If the sea level is not rising dramatically, you may have an emergent coastline. So long-term classifications now, so longer-term things at a coastline which can classify that coastline are the geology or the lithology. So the lithology is the rock type at a coast, and the structure of that rock, the way in which they're arranged, affects what type of coastline it might be. So this is mainly used to determine whether a coastline is rocky, sandy, or estuarine, which we mentioned earlier. So the actual lithology at a coastline will determine if it's hard rock, for example, that it's probably a rocky coastline, or if it's softer rock, it's probably a sandy coastline, or if there's a river, it'll be estuarine. And we've also got to consider concordant coastlines and discordant coastlines. So concordant coastlines are where the rock runs parallel to the sea, and discordant coastlines are where the rock is perpendicular in bands to the sea. We've also got longer term sea level changes and sea level rise. So as I said before, this is used to classify emergent and submergent coastlines, and tectonic plate shifts and movements can also help classify it. But climate change in recent years has been a big factor in classifying coastlines. And so as climate change continues and as sea level rise continues, we may see more and more submergent coastlines over time. So we've got two types of coast here, a rocky coast and a coastal plain. Now, rocky coasts make up around 1,000 kilometres of the UK's coastline, and they are mainly in the north and west. The cliffs there vary in height, from very high cliffs in Scotland and the west of Scotland to lower relief cliffs in Cornwall in the southwest. The geology in these places is very resistant, so the rocks are very resistant and they erode very slowly. And there is little deposition, but there is high energy erosion. So erosion is constantly taking place, but as we know, because the rock is a hard type of rock, it takes a long time for that rock to erode. And there is therefore also little sediment to deposit. Now, in a sandy plain, as you can see in the image on the bottom right here, we mainly have a flat or gently sloping relief type of coastline. And it often contains wetlands and salt marshes too. These are low energy environments, so there's low erosion rates, but deposition rates are high. They can be sand, they can be shingle, or they can be cobblestones as well. And this is most of the UK's coastline in the south and east of the UK. So places such as the south coast, particularly around Swanage, is this type of coastline. It's a sandy plain coastline. I mentioned earlier concordant and discordant coastlines. Key thing to remember with a concordant coastline, and you can draw this so you can remember it, is that the rock runs along the coastline, not in bands, but as you can see here on the left-hand side, in one consistent band. So we've got limestone here, which is a hard type of rock, along the coastline here, and that runs directly along the coast for example, in Dorset in the southwest. One continuous layer of hard rock protecting the softer rock behind it. Whereas a discordant coastline is these differing bands along the sea of hard and softer rock, so clay and sandstone or clay and limestone. So this is most of the east coast, which is a lot of our case study, and that's Holderness. And this is differing layers of resistant and soft bands of rock. And we know that the softer bands of rock here, for example, the clay, as you can see, will erode much more quickly than the harder bands of limestone. So the clay forms bays and therefore sandy coasts. And the limestone and sandstone formed headlands because of the harder rock. And we've got other concordant examples of coastlines. And you can see in the images here on the right, we've got the Dalmatian coastline of Croatia. And on the bottom right here, we've got half coastlines, which form essentially bars along the coastline because of the sand deposits. So, a Dalmatian coast, like in Croatia, is actually a coastline that has formed because of what are called anticlines and synclines, which are ridges and valleys. They've been formed over millions of years due to the harder rock that you can see on the image or the satellite image here on the right. And also what's happening is this coastline is submergent. So we are seeing the harder, higher bands of rock left over after sea level change. And that's why you have these patterns of smaller rock islands remaining. So sea level rise has left what's behind, as you can see in the satellite image. They're lines of islands that are essentially separated by narrow bands of sea. So that's an example of another concordant coastline. And we've also got half coastlines. Now, this occurs where deposition produces what's essentially unconsolidated material. So, unconsolidated rock. So, what we have is essentially a ridge, and that sand ridge forms over bays. As you can see down here, we've got the Curonian Spit that connects the Sambian Peninsula to Lithuania. And this is the Nerman Half, and that connects Lithuania to Russia. And so what's happened is deposition over time, interglacial and glacial periods too, have contributed to the amount of sediment that's being deposited in this area, and that's connected the Lithuanian coastline to the Russian coastline through the spit turning into a bar. We've also got to consider the influence of coastal dip on the rock structure and the layers of rock. So dip is the angle of the rock from horizontal. It's a tectonic feature mainly. And what happens is it produces different types of dips. So a horizontal dip produces a vertical or near vertical profile of the landscape. A high angle of seaward dip, which is over 45 degrees, which produces a slow, low sloping angled profile with one rock layer facing the sea. These are vulnerable coastlines and are vulnerable to be attacked by subaerial processes, and weathering loosens the strata in the rock here. Whereas we've also got a low angle of seaward dip, which actually produces a steeper profile of the rock, which may even exceed 90 degrees. This, as you will see, produces major cliff collapse. So if we think about our undercutting of the rock, that's the type of coastline we're thinking about here. And there is marine erosion taking place, which creates that overhang. And so the cliff is constantly collapsing into the sea. We've also got to consider the actual structures of the rock and cliff profiles themselves. So, in rocks, we get what's called faults. Now, faults are like major fractures created by tectonic plates. They create a fault line. They increase the rate of erosion, and this leads to rocks easily being eroded over time. We also got joints in rocks, and these are fractures without the rock being moved. So these are fractures not like faults. The rock has not been moved by tectonic plates here. This is because of weathering, okay, and compression. So these occur in most rocks, and they can be seen as block types of rocks, and you can see them in the image here on the right-hand side. You've got these block type structures. In igneous rock, they can form during magma cooling, and in sedimentary rock, they can form through the compression and the stretching of the rock sitting on top of each other in layers over time. We've also got fissures. These are more open than fractures, so these are more open than joints and faults, and can be found as a characteristic of most rocks on the Earth's crust. So fissures are very deep, open ravines in rock. They're deeper than joints and faults. And finally, we've got the folding that can occur in rocks, and these are bends that occur in rock. And you can actually see these bends in the image on the right-hand side here. These bends produce basically a layering effect. And the main type of that layering we can see at coastlines is an anticline and a syncline folding pattern. Now, anticlines are when the folding is upward, and synclines are when the folding occurs downward. Now, rock type in bedrock at the sea is really important. So the rate of coastal recession or retreat is influenced by rock type. It is influenced by how reactive the rock is to chemicals, whether it's a less resistant type of rock or a more resistant. So a less resistant type of rock might be considered clastic, and a more resistant type of rock might be considered crystalline. And whether the rock has any cracks or faults or fissures, etc., that we've just looked at previously. So all of these rock types have different weaknesses to them or strengths in terms of erosion and coastal recession. So let's start with our igneous rock type. So types of igneous rocks include granite and dolerite and basalt. Now, igneous rocks erode very slowly, and they also weather very slowly because the crystals within them are interlocking. So they form these X-like shapes of bands. So they bind together. So they're more resistant. And they contain very few joints and weaknesses. So these are one of the hardest and most resistant types of rocks because of the way in which they have formed. We then got metamorphic rocks. So they are things like marble and slate and schist. Now, these have recrystallized or reformed through heat and pressure from deep under earth in the mantle. They have a crystalline structure, so they're made up of these crystals, which means that they are resistant, but they are less resistant than the sedimentary rocks we're about to consider, because the crystals form in the same direction, so they are not interlocking. So they're just in a horizontal fashion. Then we've got sedimentary rocks, and these are things like sandstones and limestones and clays. And these are formed by compression and compaction over millions of years. These are the least resistant type of rock because they are heavily jointed, so they have lots of joints and cracks in them, and they have weak structures. They have moderate erosion rates in the sense that they do erode over time, but they erode faster than igneous rocks, and they erode slower. They also erode faster than some types of clays, but they do include clay as well. So because there are different types of clays, the erosion rate of those clays actually differ and vary over time. And then we finally got unconsolidated sediment or material, and this one's easy. This is just alluvium. This is just not yet cemented or compacted sand and other types of rocks. These are very easily eroded at around 2 to 10 meters per year. That's just a brief summary of how hard and soft each rock type is. Now, these rock types affect the types of cliff profiles we get. So less resistant layers or bands of rock or strata erode quickly and weather quickly. And they produce things like wave-cut notches because of the marine processes on the rock. Resistant rocks erode slowly and weather slowly. And they form what's called a bench at the cliff base. And this leads to an overhang of the cliff above. Essentially, what we've got there is undercutting taking place. So wave-cut platforms is what that bench would look like. So we've got to also consider whether rocks are permeable or impermeable, non-permeable. So permeable rocks are those that allow water through them because they're porous. They have pores like chalk. And they may also have numerous joints. Permeable rocks tend to be less resistant because weathering can take place on them much easier. So limestone, for example, weathering can take place at a fast rate. And some types of granite like feldspar can also take place at a higher rate. Now, non-permeable rocks, which are rocks that do not let water travel through them, erode much slower than permeable rocks. Okay? They're harder material. We've also got to consider at coastlines the role of vegetation. Vegetation is very important to a coastline. I'm just going to let you take 10 seconds to have a look at the image on the right-hand side here to show you the species of plant you may find at coastline. Okay, so we know that vegetation stabilizes the coast because the plant roots bind the soil together and that leaves the stems and the leaves to cover the surface of the ground and protects it from longshore drift and wind erosion and tidal erosion. Coasts are very harsh environments for plants. Because of high winds, because of the lack of shade, because of the salt water, because of the sea submerging them, plants have to adapt to the coastline. Pioneer plants, which you can see in the bottom of the image towards the coastline here, where the waves will interact with those plants, are the first type of plants to colonize our coastline. They modify the environment by stabilizing the sediment, they add nutrients to the soil, and they reduce evaporation rates because they need that water to grow. And then they create what's called plant succession. And as you can see in the image, the further you go back towards the coast where we live, the more types of different plants and communities you will find, and the stronger and more stable those plant communities will be because they're less exposed to the water themselves. And that leads us directly on to sand dune succession, or the Psammosere. Now, sand dune succession is all about how the sand dunes form stronger binds with sediment and with plants the further away from the water and the beach you are. So we first got embryo dunes. Now, embryo dunes are the smallest types of dunes that form at the coastline. They have pioneer plants and types of grasses in them. And these have to form around a large block of sediment in some way. And they alter the conditions that other plants can tolerate. So they colonize and they form a foredune over time. Now, foredunes are slightly stronger than embryo dunes. And as you can see in the image here, foredunes form more grasses. They have a higher relief rate. And then as you go further back again, the plants get stronger, the dune stabilizes further, and we get a second type of dune. We get a stronger, taller dune, and that might be a grey dune. And then we go even further back to the rear dune, and this is where we get the forest. This is where we get trees and large shrubs. And these are the strongest type of dune. They are very well sheltered from the coastline because the second and fourth dunes shelter them. So they take most of the battering from sea waves and wind from the coastline as well. And what we essentially get over time as we move further away from the shoreline, further away from the forezone, is we get stronger and stronger sand dunes. We get a climax in the plant community. So equilibrium between climate and soil is reached. So that is the Psammosere or sand dune succession. But we've also got marsh succession as well, or what's known as the Halosere. And the mixing of freshwater and seawater at the coastline or an estuary coastline causes the clay and the sand to stick together and sink. And what we get is, over time, we get a salt marsh formed through that mixing of clays and freshwater and seawater. We can also get the salt marsh drying up, where it's no longer provided water over time. And this means that these salt marshes can actually form, as you can see in the image down here, sea lavenders and cordgrass and other types of smaller plants. And these plants, again, very much like with sand dune succession, form stronger over time the further away from the coast you go. Soil fertility also improves the further away from the coast you go as well. And when all the rainwater washes out all of the salt on the salt marsh, this is when we allow plants to start colonizing in a more strong way compared to under the sea. In the UK, the climax community is normally deciduous oak forest, the furthest point away from the sea. And in Scotland particularly, it is coniferous pine forest. Now that is a brief roundup of everything in EQ1 for coastal landscapes and change. The key thing with EQ1 is that it's mostly theory-based and it is just general knowledge. So what you need to do is make sure that you go back over this numerous times, that you look at sand dune succession and salt marsh succession, and that you look at the basics of rock lithology, the basics of how rocks are formed, and the weaknesses and strengths of those rocks at different coastlines. I hope that was useful for you in some way. The next session will be on EQ2, and that will be looking at the characteristics of landforms at coastlines. Please do use your coast revision booklet to go over these sections of coastal landscapes and change, and I will see you in the next one.